Okay, good afternoon, everybody. Um, Before starting the lecture, let me just say something about exam and the grading scheme. You remember like 25% is for exam 1 and 25% for exam 2. And I think 25% for project and the rest for homework and quizzes and stuff. So what I'm going to do, because I told you if you do a better job on the second exam, I definitely consider that improvement, okay? So when I calculate your grade for exam, I'm going to have 3 sets of weights. One is 25-25, the other one is 35%. This is exam 1, let's say, and this is exam 2. And I'll also go with 35-15, okay? So I calculate your grade based on these 3 sets of weights and find the maximum. Okay? So in this case, if you do a better job on the second exam, then the weight for the second exam would be better, would be higher actually. Okay? That's one thing I think many of you had concern about. Okay, what I did poorly in the first exam, what should I do? Should I drop it or not? I cannot answer that question, but I can tell you this is the way I'm going to basically calculate the exam grade. Okay? So, any questions? You good? Okay. So, back to lecture. Hypothesis testing for the variances of 2 normal population. As you can see, this is the null hypothesis, this is the alternative hypothesis, and we said we use F statistics because we know under H null, S1 squared divided by S2 squared follows an F distribution with n minus 1 and n1 minus 1 and n2 minus 1 degrees of freedom. Okay? Therefore, these are the critical regions that we have, and this is basically the confidence interval. For the confidence interval method, if one includes actually, if one belongs to this confidence interval, we do not reject H null, otherwise we reject H null. Okay? This is for two-sided, this is for one-sided greater than, and this is for one-sided less than. We had one example, and the last basically type of hypothesis testing for 2 population is for Bernoulli populations. Okay? You have 2 Bernoulli populations. So P1 and P2 is the percentage of, let's say, non-conforming items in the first one, and the second population you want to see if they are equal or not. Or the percentage of female in one population and percentage of female in another population. You want to see if they are equal or not. In that case, your null hypothesis is equality of the proportions. Okay? And the alternative is either they are not equal or one-sided, which is greater than or less than. Okay? What is our test statistic? We know that P1 hat, which is what? Do you remember? So let's say this is the first sample. This is the second sample. We call it like x1 and x2. Let's call it x11, x1n, and x21 up to x2n. If I have 2 independent samples, P hat 1 is what? Is summation of this divided by n. In this case, n1. Let's call it this guy n1 and this guy n2. So it's x summation of xi divided by n1. And over there we denote it by x1n. This x1 is the number of successes in the first sample. We can calculate P hat 2, which is x2 divided by n, the number of successes in the second sample. And we know that these two, if n is large, n1 and n2, both of them are large, they follow a normal distribution, okay, based on central limit theorem, approximately. So what we can do, we can say the difference between these two, because these two are independent. Why? Because their samples are independent. That's the main assumption. The difference also follows a normal distribution. Okay? And this normal distribution has basically this mean. And what is the variance? The variance should be the variance of this guy plus variance of this guy. Okay? You remember that? Let me just write it down. The variance of the first proportion plus the variance of the second proportion. Okay? Now, let's see how this changes under H null. So what does it mean? If H null is true, what's going to happen? So if H null is true, what does it mean? P1 and P2 are equal. Okay? So I can say P hat 1 minus P hat 2 follows a normal distribution with mean 0 under H null. How about this guy? If P1 and P2 are equal, their corresponding variances also should be equal. Okay? So now you can see I have two samples. Both of them are trying to estimate same variance. Have you seen this situation before? Pooled variance estimator. So I have two samples trying to estimate one variance. Okay? So what I can do, I can combine them for estimating the variance. And this is the way that we combine them. So we find one P hat. So combining them means, if you combine these two samples, how many bad parts or how many basically successes you are observing, divided by total number of samples. And you use this P hat for estimating the variance. So variance would be this guy divided by or multiplied by. Okay? So under H null, this guy is my variance. Again, this is different from the variance that you used for confidence interval of these two populations. You remember? If I go back and find the slides, let me do that because it's important to see. Two populations. Maybe it's here. Yeah. Confidence interval for two populations. So look at the confidence interval. So that's the confidence interval I'm using. That's exactly this guy. Okay? However, when I'm doing hypothesis testing under null hypothesis, that can be reduced to this guy. Over there, I cannot do that because there is no null hypothesis in confidence interval. Okay? Here, I have null hypothesis, and null hypothesis saying that P1 and P2 are equal, therefore their variance is equal, therefore I can combine the information of two samples to get a better estimator. This estimator is definitely better than the individual estimator. Yes?
If you have two populations that have identical, that are identical, how is it two populations and not just one population?
They are identical in terms of, oh, you mean like P1 and P2 are equal, for example?
Yeah.
Okay. Yeah, so you can say then these two populations are similar, are exactly the same. So you can combine these two populations.
Okay.
Yeah. That's basically the thing that we are trying to do. We want to see if these two populations are the same thing or not. Yeah. Yeah.
Okay. So you
Exactly. And that question is translated to P1 equal to P2, which is the hypothesis testing that we are trying to test. Yeah. Any other question? Is it clear what we are doing? Basically the combine or estimate for P and the variance. Any questions? You see the difference between the confidence interval and hypothesis testing here? Okay. Okay. Now, based on this test statistic, which is Z0 and follows a standard normal distribution, everything else is going to be very similar. So I can use Z0 and compare it with these thresholds. I can use confidence interval method. By the way, the confidence interval here is different from the regular confidence interval because I'm using that pooled estimator. Okay? Or I can use p-values. Either is fine. Any questions? You good? Okay. One example. Let me give you a couple of minutes to work on that. Yeah. Yes, yes. Okay, so we have one treatment method for depression, and another one is placebo. Then we want to see if there is any difference between these two. Therefore, we just want to see if these two P or proportions are the same or not. So we have 200 patients. They are randomly and evenly distributed or assigned to two groups. So that's the summary statistic of the first group. 19 out of 100 got better. For the second one, which is the actual treatment is 27 out of 100. So p hat 1 and p hat 2 is calculated. And p hat, this is basically for variance, is 19 plus 27 divided by 100 plus 100 using this equation. Okay? So what should I do? I need to find Z0, which is p hat 1 minus p hat 2 divided by the standard deviation. And if we calculate this guy, that would be 1.35. So alpha is 0.05. So Z alpha over 2 is what? 1.96. So the absolute value of Z0 is less than Z of alpha over 2. Therefore, we do not reject H null. There is no difference between these two. Okay? Yeah. Question? What?
Effective in treating. So the there should be.
Let me read it. Let's see. Yes. So the question is, I just repeat the question for video students. Sometimes they cannot hear your questions. So the question is, shall we use basically the one-sided hypothesis testing and saying that the method is better? So something like this, because we want to see whether St. John's wort method is effective or not. I think yes, that's correct. That actually would be better method to do. I don't know why the textbook did it as two-sided, but I agree with you. I think if we want to see this method is more effective, we should say this guy is greater than this guy. So in that case, yeah, you end up with Z point. So Z0 would be, oh, by the way, let's see. Your Z0 would be, oh, that one is negative. Yes, you're right. Yeah, that one is negative. And we want to see, just want to make sure that, yeah. And your number is Z.05 is 1.645. And you compare it with, if it is less than, you compare it by this guy, Z of minus Z of alpha. In this case is this guy is not less than this guy. Therefore, we do not reject. Conclusion doesn't change. Okay? But yes, that's the better way to do that. You had a question also? The same question. Okay, good. Good. Yeah, that was a very good point. Yes?
Like, does it matter which one you defined as P1 and P2? Does it change the sign?
No, the question is, does it matter which one you define P1 and P2? Yeah, they change the sign, but also it changes at the same time the criterion that you're using for the threshold. Do you know what I'm saying? Yeah, exactly, exactly. So it doesn't change at the end of the conclusion. Yeah. Question?
Had stuck with the equal or unequal to see if just the placebo versus the St. John's wort makes any kind of difference. Whether your Z naught was negative or positive, could that have determined which end it was?
If you reject
better.
Yeah, that's actually a good one. The question is if it was basically two-sided, then if we rejected H null, then could we use basically the sign to see which one it would be better? Yeah, you can, but I would redo, if you want to see which one better, I would redo the one-sided. Okay? Yeah. Any other questions? Okay, good. So, I have one question for you guys. Yeah. So what if we basically ask patients to do both of them? Okay? One is placebo and the other one treatment. Okay? And then record. So in that case, our sample size and one would be 200 and two would be 200. So how would you change your experiment if necessary? Do you think it's necessary to change the experiment? Or, I'm sorry, not the experiment, the hypothesis testing. Why it is necessary? You want to say something? Yeah. Because you were saying yes.
Because you would have sort of like the dependencies now on solutions, so
correct.
You probably want to do a pair test.
Exactly. Here also we can do a pair test because if you are using all 200, both of them are basically going under the St. John's wort treatment and the other one also, and also the placebo, then you have for each patient, patient 1, you have method 1 and method 2, and then you have 1, 0, 0, 1. So it's kind of like paired. And they are dependent. Why this column dependent to the second column? Because you are using the same patient for both methods. So what you can do, you can basically also extend that pair T to this situation as well. Okay. However, here is going to be pair Z or something like that. Yeah. Go ahead.
So, be able to do that knowing in this case the treatment is actually changing the person. Measurement wouldn't actually change the specimen.
Yeah, I mean, maybe in this case it's not possible. Yeah. But what I'm saying is if you see the dependency, yeah, maybe actually this is impossible to do in real world for this case because of the type of situation. Okay. So let's see how to calculate beta error for this case. I don't go through the details. The equations are given. Just one thing is this P1 minus P2. I'm sorry, this PQ bar. So P bar is 1 minus P. Okay? And Q, I'm sorry. Q bar is 1 minus P bar. And your P bar and P hat is the same thing. Okay? So it's x1 plus x2 divided by n1 plus n2. That's one piece of information here. And your sigma p hat minus p hat 1 minus p hat 2 is this guy. Okay? So you know alpha, you know n1 and n2, you know p bar and q bar, and then you just plug in and you know the sigma. Just plug in everything else, everything here, and then you get the beta. This is for two-sided beta, and this is for one-sided. Greater than and one-sided less than. Okay? Any questions? Yep.
Probability of failure?
P bar is the probability of failure. Oh, yes, yes. Psych says, yeah, P bar is the estimate of the pool estimate. Okay? So under H null, P1 and P2 are the same. Okay? So the question is, what Q bar means. All right? So that's the question. So what Q bar means. Under H null, P1 and P2 are the same. Okay? So what we do, we combine the sample to estimate P hat. Okay? Because both of them are the same. This P hat is the probability of success for both population because the same. Okay? And Q bar is 1 minus that P hat, which is the probability of failure, as you mentioned. Any other questions? We good? Yep.
Under rational, P1 minus P2 can be substituted as 0 in this equation.
Okay, so the question is under H null, P1 minus P2 can be replaced by 0. Yes, but when you calculate beta, it's not under H null. Because beta, the definition of beta is under H alternative. Okay? Any other questions? Yes.
Reject H naught. We're saying that the null hypothesis is valid.
Yes.
And so then we're saying that the treatment doesn't have an effect.
Yes. So in the previous example, when we said we do not reject H null, which it implies that the treatment doesn't have an effect. Yeah, that's correct. Okay. So choice of sample size. So it's a little bit ugly, the equation. But anyways, to gain power 1 minus beta under alpha, then what you do, you use this equation. And this equation, I think this is a little bit wrong because this should be approximate. Okay? This is not exact. And again, Q1 is the probability of failure for the first population, and Q2 is the probability of failure for the second population. Okay? Any questions? You good? Okay. So we are done with basically two-sided hypothesis testing. New topic is called analysis of variance. Okay? And so what is the main purpose of analysis of variance? The name is analysis of variance, but the main purpose is to test mean. Okay? So you know that like if you have mean of one population, how to perform hypothesis test for mean of one population. And you learn for mean of two populations. Now the question is, what if I have mean of more than two populations? Okay? How I can perform the mean test for more than two populations. Here is one example. Let's say a manufacturer of paper used for making grocery bags is interested in improving the tensile strength of the product. And their product engineer thinks that that tensile strength is a function of hardwood concentration. Okay? And the hardwood range is from 5% to 20%. They want to try 5% concentration, 10%, 15%, and 20%, and see if there is any difference between the tensile strength of produced paper bags or not. Okay? Does it make sense? So they have one factor they want to, that's the main purpose, is hardwood concentration an important factor in improving tensile strength. Okay? How we can answer this question? By one hypothesis testing. So Mu1 means the average of or the mean of paper produced with 5% hardwood concentration. Mu2 is the average of basically tensile strength when the paper is produced using 10% concentration, and so on and so forth. Okay? If this average is equal, okay, if we cannot reject H null, what is the conclusion? There is no difference, therefore hardwood concentration is not an important factor. Does it make sense? Okay? So, what is H alternative? At least one of them is different. Maybe mu1 is different from others. Maybe mu2 is different from others. So, the main purpose of ANOVA is to do this hypothesis testing. Is it clear? Why do we use ANOVA? Okay. So let's just start with the type of data that basically we collect for performing this hypothesis test. We have different hardwood concentration, 5, 10, 15, and 20%. And we make paper bags. For each of them, we make 6 paper bags. And we measure the tensile strength. Okay? So these numbers inside the table is the tensile strength when the paper is produced by 5%. This is another paper bag. So the tensile strength of another paper bag when produced by 5%. Does it make sense? So how many paper bags I'm producing? 6 for each concentration. Okay? Any questions so far? What is very important? Experiments should be done in a random order. Okay? Do not start with 5 and complete this row and then go ahead and complete the second row. No. Everything should be random. You do this experiment first, probably the second one here, the third one here, the fourth one here, you know. How many experiments do you have overall? It's 24. So you have 24 numbers. You can randomly generate a random order, and then based on that, do the experiment. You have a question? Because the question is why randomness is important. Let me give you, actually I can use this example as well. So let's say you start with hardwood concentration, okay, and you produce papers, okay. At the beginning, you just start the machine, okay, production process. You start and you work with, you produce this number, this number, this number, or the first 6. But when you start for the second row, like producing paper for the 10% concentration, then the temperature goes up because machine has been working for a while. So over time, temperature is increasing. Okay? So there is another factor that basically you are not taking into consideration, which is temperature. This is just one hypothetical example. And that factor could affect your response variable, which is the tensile strength. But when you do randomized, okay, the effect of temperature is going to be dissolved. Okay? Why? Because it's not just doing the 5% on the normal temperature and 10% on the higher temperature. Some of those 5% on the normal, some of the 10% is on the normal, some of the 15% is on the normal, and some of them on the high temperature. So the effect of temperature is going to be vanished if you do randomly. Okay?
I mean, test them in random order?
No. Producing the data.
Okay.
Collecting the data in a random order. Yeah. Collecting the data in random order. Exactly. In this case, collecting data means producing and testing. In some cases, there is no production. It's just testing. Okay. So, some basically definitions. The levels of each factor, this is called factor. And the tensile strength called response. Okay? So the levels of this factor, sometimes called treatments. So levels means 5%, 10%, 15%, 20%. Sometimes we call it treatments. Each treatment has 6 observations, and here we call it replicates. Okay? So how many times we are replicating the experiment. and the runs should be we should do the random experiments, and sometimes we call this setting by completely randomized single factor experiment. So it's single factor experiment because we're only considering one factor, and it's completely randomized. Okay, so let's do that. Let's start with descriptive statistics, a visual tool which is called what? Do you remember? Box plot. So for the first population, second population, third and fourth. So based on box plot, there is a huge difference between these two. Okay, between these levels. So basically, increasing your concentration can improve the tensile strength. Okay, so these are the concentration x-axis, and y-axis you have tensile strength. But can we show it statistically that this difference is significant? Okay, so again, another type like notations, another set of notations. So the number of populations or number of levels that we have. Okay, so here we have how many levels? 4. We use A to denote that, and I is the level that we are interested in. So I is from 1 to A. J is the index for the sample size or replicates. In this case, is 1 to N. So Y 1, 2 means the first treatment, the second experiment. Okay? So Yij is observation J from population I. Okay? So again, population, treatment, factor level, they are the same thing. Okay? Population, treatment, factor level. So another set of notations, when we do the row summation, okay, we do row summation, we denote it with Y that row dot. For example, this guy would be Y1 dot. Okay? This guy would be YA dot. And the averages are Y bar 1 dot. So this is also a set of notation. The grand total, which means summation of all numbers, is Y dot dot. And the grand average is Y bar dot dot. Okay? We are going to use this notation later. Now, let's see what statistical model we are going to use. So let's start with one observation. Oh, by the way, this is the plot of this tensile strength. So we have 4 populations. So these are the mean for the first population, mean for the second population, third and fourth population. See that? Okay? So this is Y11, and as you can see, Y11 can be represented as the average for the first population or level plus some random error. Okay? So I can write down a linear statistical model for that. So your Yij, again, I was index for population, and J was index for sample. Okay? Would be, so Yij coming from the ith population, which is mu, plus some random error. Okay? Is it clear? Now, what is the relationship of mu I or mu 1 with the grand or overall mean? As you can see, mu 1, so let's say this dashed line is the overall mean. Okay? So put everything together and the grand average. Let's say something like that. Okay? So you can see the overall mean and mu 1 is different. Okay? So this difference we denote it by tau 1. So your mu 1, or in general mu I, is grand or overall mean plus the deviation from that mean, tau I. Okay? So if I combine these two, this is the linear statistical model I'm using to explain the data. Okay? How the data is generated. Each observation is coming from an overall mean, effect of population, which is the effect of level, in this case, effect of what? Concentration level, and some random noises. Does it make sense? Is it clear? Any questions so far? You good? Yeah.
There seems to be an assumption that tau I are going to be distributed in a Gaussian manner. Why is that?
So the question is there an assumption on tau I? Are there random variables or basically deterministic variables? So ANOVA is one part of a very big course or big domain which is called design of experiments. Okay? In this class, we assume that tau i's are not random, discrete. But there are some methods which assume that like basically tau I are random variables, and there is another basically way for analyzing the data. Okay? So what is the basically assumption? Here are the assumptions that we have on the model. Any statistical model that you have, basically it comes with some assumptions. So first of all, those random noises are NID. Okay? Normally independently distributed. They should be independent. And these variances for each population, because you know that, for example, let's say this is mu1, this is mu4, okay? So there is one normal population here, one normal population here. You know, their mean are different, but we assume their variances are the same. Do you remember we had this assumption before for 2 population t-test? That's basically the generalization of that assumption. So we have more than 2 populations, but we assume the variances are equal. Okay? That's basically assumption. And another assumption is, the last assumption is basically the summation of tau I. So what it means, summation of tau I is equal to 0. It means that this difference is negative. Okay? I'm sorry, this difference is positive. This difference is negative. For example, mu3 mu1 minus mu is tau1, tau2 is mu2 minus mu, tau3 mu3 minus mu, and tau4 mu4 minus mu. Some of them are positive, some of them are negative. Okay, in this example, I would say mu1 is negative, mu2 is negative, mu3 is positive, mu4 is positive. So summation of these are 0. That's also the main assumption. Okay? Any questions? Is it clear? Now let me ask you a question. So let's say H null is true. Okay? So what happens to tau i's if H null is true? 0. I'm not talking about the summation. Summation is always 0. Okay? I'm talking about individual tau i's. Okay? If all mu's are the same, which means mu1 is equal to mu2 is equal to mu3 equal to mu4 and equal to overall mean, then all tau's are equal to 0. Therefore, what I can do, I can basically reduce my hypothesis testing from mu1 to up to mu4 equal to 0 to tau. I'm sorry, mu1 equal to mu2 equal to mu3 and mu4 to tau 1's or corresponding tau i's are equal to 0. Okay? And that makes sense also algebraically. If mu1 is equal to mu2 is equal to mu3, mu4, I just write down, I know mu1 is what? Mu plus tau I tau 2, tau 3, and tau 4. So basically, when they are all equal, they are the same as overall mean. Okay? Equal to mu. Then subtract mu. All of them become 0. That's simple. Okay? Any questions? So let's see how we can do the analysis. So we are done with the notations and assumptions. So here is what we do. Okay. Let's say we have, this is basically the all observations that we have. And we know how we can calculate the total variation. Total variation means what? Each observation minus the overall mean. This is the grand average, which is the estimate for overall mean. Okay? The grand average means what? All observations together take one average. So I can basically use this and calculate sort of total variation. Okay? And this is the equation for total variation. Each observation minus what? The grand mean and summation over number of levels or populations and the number of samples. So basically what it means, subtract each point from the grand average, square that, and add them up. That's it. That's total variation. Okay? And I don't know if you remember, we used to use very important equality. Yes. Do you remember that? So these two are very similar. So we can show that this can be decomposed into two parts. Okay? This is very similar to this guy. This is just for one population. This is for more than one population. Okay? But the interpretation is very important. So let's see what it means. This guy here is total variation. Okay? This guy here is total variation. How about this guy? What is this? The average of each population. What is this? The average of the overall average. So the difference means the variation of each population from the overall population. So we call it between population variance. Okay, or variation. Or between group variation. Okay? So basically, again, we're almost out of time. I'm going to wrap it up very soon. So it's this guy. So this is for population I, subtracting from overall. So population I. Difference from population I, the average of or mean of population I from overall average. So this difference is a between population variation. How about this guy? So each observation subtracted from its own average. So what is this? I go back. So that's an epsilon, exactly. So each observation minus its own average. So it's called within population variation. Okay? Why? Because let's say this is one population, each observation minus grand mean. So each population minus, I'm sorry, not grand mean, its corresponding mean. So it gives me within group variation. So you can see the total variation can be decomposed into two parts, between group variations and within group variations. Okay? Then we continue on Friday. I'm going to review that part again and see how we can use basically this decomposition to set up our hypothesis testing.